When writing functional scripts, you often end up juggling dozens of isolated variables, names, dates, and numerical values scattered across memory. Managing them individually invites chaos, but if we bind those related pieces of data together, they form a single, stable entity. Built-in data types like integers and strings cover the basics. Python's real strength lies in its extensibility, the ability to invent entirely new, custom data types to handle complex information when the defaults fall short. We do this by writing a class. A class acts as an architectural blueprint, permanently bundling specific state data and the behavioral functions that operate on that data into one cohesive package. Rather than just memorizing syntax, we are going to trace exactly what happens in the Python memory heap the moment a custom object is born. Building an accurate mental model of object reference mapping is the dividing line. It marks the transition from stringing together procedural scripts to engineering reliable software. We will trace this process using a simple custom account class, tasked with securely managing a user's name alongside a financial balance. Understanding how memory is allocated during this instantiation phase is the foundational step in mastering object-oriented architecture. Every custom type begins with the class header. Class account establishes the starting point for our new data type. Crucially, this definition holds absolutely no user data. It exists entirely as a structural guide, outlining the shape of future accounts. To create an actual account for John Green with a starting balance of $50, we write a constructor expression. Executing this commands Python to read the blueprint and allocate a fresh, isolated block of space directly in the memory heap. We pass our specific starting data into this constructor as arguments. Notice the deliberate use of the decimal class here, which guarantees strict financial precision, avoiding rounding errors common with standard floating point numbers. Syntactically, the parentheses following the class name are mandatory to trigger the process. Even if an object requires no initial arguments, those parentheses are the strict trigger forcing instantiation. This sequence of operations builds complex architecture from scratch, a process vastly different from a simple variable assignment like x equals 5. But right now, the new object sitting in memory is entirely inert. It is an empty shell, completely lacking the specific state we requested. The mechanical question is how those arguments actually route themselves into this newly allocated empty memory block. Constructor expressions bridge the gap. They translate an abstract structural blueprint into physical memory allocation, preparing the system for state initialization. Immediately after allocating memory, Python automatically fires the initialization trigger, the __init method. The first parameter, self, represents the specific object instance. Python implicitly captures the memory reference of the new object and passes it directly into the method. Developers never manually pass an argument for self. The interpreter handles it quietly to ensure the initialization logic always maintains the correct context. With that connection established, dynamic attribute assignment begins. The command self.name equals name writes the provided string straight into the object's internal namespace. A parallel execution happens for the account balance, locking the precise financial value into the instance. The init method also serves as the object's primary validator. It houses the logic that ensures the starting state is actually valid. Before accepting the initial state, the method runs a conditional check. If the requested starting balance is less than 0, the initialization process halts entirely. Raising a value error acts as a strict systemic shield. It kills the creation process immediately, ensuring an invalid object never enters the broader system. Python enforces a strict constraint on this method. Returning any value other than none from init triggers a fatal type error. Its sole purpose is internal setup, not returning external results. Self operates as the implicit umbilical cord. It allows a nascent object to securely populate its own internal namespace during the chaotic split second of creation. Once the object is initialized, state mutation must be carefully controlled. We do this by invoking methods like deposit. Just like initialization, deposit relies on self to map its logic back to the exact memory location of the account we want to alter. Methods act as active gatekeepers, guarding the internal data integrity of the object. We can see this in the method's defensive validation. a hard check designed specifically to catch negative deposit amounts. If a flawed instruction arrives, like a negative $123, it is systemically rejected. The input hits the logic barrier and shatters. The resulting traceback error is a deliberate protective feature. By stopping execution, it forcibly preserves the strict mathematical integrity of the financial ledger. When a valid, positive value is passed, it clears the checkpoint effortlessly, merging with the balance and updating the object's total. Notice the architectural shift. The object mutates its internal state according to its own rules, rather than letting an external script freely overwrite its variables. Methods provide armored interfaces. They enforce strict operational boundaries, keeping state secure entirely without external intervention. In our account example, the name and balance are themselves objects belonging to other classes. This reveals a fundamental aspect of Python's architecture. Complex objects are often built by referencing other, simpler objects. This clarifies our model. The account1 block does not physically contain the string text John Green or the numerical data. Its attributes are merely references, directional pointers aimed at entirely separate string and decimal objects existing independently elsewhere in the memory heap. In software design, this structural pattern is defined by a specific technical term: composition. Composition defines a has-a relationship. An account has a name and has a balance. This replaces the flawed mental model of physical containment with a web of connections. Relying on pointer-based references is highly efficient. Instead of duplicating raw data and wasting space every time an object needs it, the system simply points to a single instance of that data. By nesting these references, we construct sophisticated software where individual components interact by simply pointing to one another. Each manages its own small piece. A Python object is a master coordinator of references. Understanding this lets you stop writing linear scripts and engineer highly reliable, secure architecture.